Hello everyone. So we have the following problems here. We're going to find some vertical asymptotes for the following functions. G of x equals e to the x divided by quantity 2 sine x plus 1 on the interval 0 to 2 pi, including 0 and not 2 pi, and the function x ln x. Okay, so you might have seen the topic of vertical asymptotes before in a pre-calculus class, or with speaking of rational functions. So rational functions are basically functions where it's one polynomial divided by another. So for example, 2x squared minus 1 over x plus 5. And there is a way of finding vertical asymptotes for those types of functions, as by like factoring and like canceling and such. But you have this situation here where that doesn't apply, because you have two functions that are not rational here at all. So how do we deal with that situation? Yeah, you can still have certainly vertical asymptotes here. And the thing to look at is what I have written here, where it says you have a vertical asymptote that occurs when the limit as x approaches x naught of a number, either from the left, the right, equals either an infinity or negative infinity. Okay, so it doesn't have to, a lot of people think it has to be from both directions. It's an infinity. Now it doesn't have to be both, it can be just one. And let's start with e to the x divided by quantity 2 sine x plus 1. So first of all, which points should I be taking a limit at is the first question I ask. Well, you'd have to look at where we have our quote-unquote problem points. So that is when the denominator is equal to quote-unquote 0 here. So 2 sine x plus 1 is going to equal 0. That's where I would have my problem, because you have a fraction here, function, and you know, when does that have a discontinuity? When the denominator equals 0. So that's what I'm going to be looking at. I'm going to look for the denominator equal to 0, and you would get sine of x equals minus a half. And if you were to solve that on the unit circle, that's 7 pi over 6 and 11 pi over 6 for points between 0 and 2 pi. Okay, so what we're going to do is as follows. We're going to go ahead and take a limit as x approaches. Let me start with 7 pi over 6 from the, let's say, left. Why left? Well, just because it's up to you to choose the direction. It could have been from the right as well, but I just chose the left. And based on that, I will go ahead and find my limit, okay, and see if I get an infinity or negative infinity, then I can claim that. Okay, so how do I approach this? Well, a couple ways of doing this. You can do this analytically speaking, look at numbers, or I can look at this graph as well. Now, as you approach 7 pi over 6, and if you approach it from the left, you're coming in this direction. Yeah, 2 sine x plus 1 gets really close to 0, but if you notice, these numbers they get close to 0, but they're still positive though. And you would get, like on the bottom, it looks like numbers that are close to 0 and positive, and on the top you have like whatever e to the 7 pi over 6 is there, some number. Anyways, when you have a number and you divide it by numbers that are getting like so small to a point, you get like an infinity or negative infinity. And in this case, it's a positive infinity, because the numbers on the bottom, yeah, they look like 0, but they're positive. And then on the top, e to the 7 pi over 6 is what this number that you get for e to the x, that's what e to the x approaches, that's positive. So you get an infinity, and therefore you have a vertical asymptote at 7 pi over 6. And you would basically now do the same thing and taking the limit as x approaches 11 pi over 6. And again, you can do it from the left or right, it does not matter. Let's say you were doing it from let's do the left. And if we did that now and we focus in on the graph at 11 pi over 6 right here, as you approach 11 pi over 6 from the left, the function 2 sine x plus 1 looks like it's close to 0 again, but it's small negative numbers is what you have. And this would now look like 0, close to 0, but small negative numbers. And then the e to the x would look like e to the 11 pi over 6, which is just, some number. So we have a number that's positive divided by numbers that are really small, that are and they're negative. So you're going to get a negative infinity here. So you get another vertical asymptote at 11 pi over 6. Now, one thing to note is that if you're drawing out a picture, if you're told, hey, can you draw this picture out for me? I would need to know what the limit is as it approaches the left and right of 7 pi over 6. Because, yeah, I know the behavior when you approach 7 pi over 6 and then 11 pi over 6, but from only one direction. If I want a graph, I would need for both, so just keep that in mind. But for the purposes here of just finding a vertical asymptote, that's all we need to do. Okay, and then, yeah, we can move on now to our next function, which is x ln x. And we're going to do the same thing in the sense of we're going to try to find problem points. Now, this function has a domain of not including 0 to infinity. X itself can take any value, but ln of x only takes things that are positive, okay? So 0 to infinity is going to be our domain. What are the quote-unquote problem points? Well, for me, I would say it's 0 could be like the quote-unquote problem point here because that is on the edge of the domain here. And that's possibly, yeah, that's something I can't plug into ln of x, so that's telling me, yeah, that would create some kind of behavior that would go towards infinity of sorts, maybe, you know. So again, it's you look for places where you have those issues. Now, if you take the limit as x approaches 0 here from the, and it's going to be from the right, yeah, because if I have 0 to infinity as my domain, I can only approach 0 from the right because the function doesn't exist on the left. So x ln x. Now, if you take this limit, you get the form of 0 times negative infinity. As x approaches 0, ln of x, do you remember the graph of ln looks like this? Ln approaches negative infinity, x approaches 0. So it's going to be a what we call an indeterminate form. And that means that, look, I need to do some more work to find the limit. A lot of people say, oh, the limit is 0, but that's not the case. It's indeterminate, and what's the work that you do? Well, often, and I have another video on this channel if you'd like to watch, when you get to this case, you have to do L'Hopital's rule pretty much. And when you have the case of 0 times negative infinity here, what you do is this. You're going to make a fraction, and you keep one of the functions on the top, so the ln of x will stay, and you rewrite the other function as 1 over that other function on the bottom. This is equivalent to this. If you do a little bit of algebra, maybe pause this video, you'll see that they're the same. And the reason we're doing this is so when we approach 0 from the right, you get infinity here over negative infinity over infinity. You get an indeterminate form where you can use L'Hopital's rule, so that's why we needed to do that. And when we approach 0 from the right here, the derivative of using L'Hopital's rule, ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Flipping the minus 1 over x squared to the top will give us minus x total after you simplify, and that limit is 0. So in this case, we do not have a vertical asymptote because the limit gave me a value that was in this case, just a real number, 0. You only have a vertical asymptote if it was infinity or negative infinity, okay? But there you go. That's pretty much how you approach these types of functions that are not rational. You go ahead and you take limits as x approaches a value, and again, you look for those problem areas. All right, well, thank you for your time. Hope this helps.